The goal of this video is to shatter the old way you've been thinking about data structures and show the right way of thinking about them, which is much simpler. Everyone knows the array where we just store our data in sequence, but this is actually a really bad way of looking at arrays. A better way of looking at them is this. When you say X in your programming language, the computer isn't giving you the whole array. It's really just giving you the root node of the array, which is this node here. From the root node, you can step along any of the labels in O of 1. So you can step along the 0, or the 1, or the 2, which gives us O of 1 read time for the array. You can also see why we have O of n write time. If we remove the first element, so we remove this 0 here, arrays always need to start with 0 and end with n minus 1. So we need to update all of these labels. This needs to become a 0, and this needs to become a 1, and this needs to become a 2. And that's O of n in general. I know you know what an array is, but the goal here was just to show you that an array can be represented really well as a directed graph, and we'll see that as we go through the other data structures too. Let me just fix up our picture here for a second. Now let's move on to the linked list. The way you come up with a linked list is to try and improve the array. Say we want to insert the letter G into the second slot in the array, like this. And that corresponds with inserting a G like this and then changing all the indices after the G. What can we do to avoid that? Instead of shifting everything over, why don't we just record some pointer from B to G and then another pointer from G to 15? And that way we don't have to shift everything over. That's exactly what a linked list does. So the linked list of this array that I've just drawn would be this. Let's just clean everything up. You can see that now when we go to add the G, we don't have to shift anything over anymore. All we have to do is update a couple pointers. Now the cost of adding or removing an element is O of 1. But what about the read complexity? Now when we say L of 3, for example, we can't just immediately access the third element. When we say the data structure's name, L, we start at the root node. And to get L of 3, we have to step 3 times. 0, 1, 2, 3. And that's the only way to get the third element. And just to remind you, for the array, we had O of 1 read complexity and O of n write complexity. So if I just clean all of this up here, then these are our results so far. We have the array and the linked list. For the linked list, it's also sometimes helpful to go the other way. So sometimes you want to be able to start at the end and go backwards. So all that means is that we add a pointer to the end and we add pointers in the other direction. So say we're standing at this node. We can say this node.prev and follow the arrow here to go here, or we can say this node.next and follow the arrow here to go to this node. That's called the doubly linked list, or the double-ended queue, or the DQ. You can see that both of these had an O of n cost somewhere. This had the O of n in the write, and this had the O of n in the read. And that's actually not a coincidence. I haven't seen it proved anywhere, but it's really easy to show that anytime you allow any element to be indexed arbitrarily, you need an O of n cost. So that brings us to our next data structure, the stack. To avoid that O of n, a stack is where you only read and write from the end of your array or your doubly linked list. If we're using an array, it looks something like this. Then we can always access the last element in O of 1. We just step to the last element. Similarly, we can always add a new last element in O of 1. We can just add, say, E. And we can also always remove the last element in O of 1. All the operations for a stack are O of 1. Queues are very similar, but rather than reading and writing from the same end, we read and write from different ends. You need to implement a queue as a linked list or a doubly linked list. An array won't work, and if you think about it for a couple minutes, you'll realize why. It has to do with this O of n write that the array has. So if we add some element, say E, all that means is that we have to change the head to point to it, and then we have to update a couple pointers. Similarly, if we remove the last element, it's as easy as changing the tail to point to the second to last element and then updating a couple pointers too. So you can see that even though stacks and queues store elements in order, so there is a first element and a second element and so on, all of the operations for them are just O of 1 because we only choose to look at the first and last elements. Let me just clean this up a little. Those are all the ordered data structures you need to know. And just to recap, the array in the doubly linked list had O of n because they indexed elements arbitrarily, and the stacks and queues had O of 1 because you could only access elements from the start or the end